In section 20.3, we'll start to look at oxidation and reduction, particularly as it relates to carbonyls. So the most useful way of examining oxidation and reduction with organic molecules typically is to think of oxidation as a decrease in the number of carbon-hydrogen bonds. Therefore, reduction would be an increase in the number of carbon-hydrogen bonds. So we can look at a few examples and then try to decide whether each of these reactions would be an oxidation or a reduction. So here I lose this carbon-hydrogen bond and it's replaced by a carbon-oxygen bond, so this is an oxidation. If I take a ketone and I convert it into a secondary alcohol, I have a new carbon-hydrogen bond, so this reaction would be a reduction. And I think this is a very useful way of looking at it because sometimes we can be confused by the idea of oxidation and to think that somehow oxidation means oxygen since they have a similar sound. And if I look at an example where I take an alkene, convert it to an alcohol, I've added an oxygen. However, the product has one more hydrogen than the starting material, so this overall is a reduction. Okay, remember, it's not directly tied to the number of oxygens. Oxidation, even though it sounds like oxygen, and sometimes it works that way, like in the earlier examples, it did work that way, but that's not a good rule. So the rule that's useful with organics is here. An oxidation has a decrease in carbon-hydrogen bonds, a reduction has an increase in carbon-hydrogen bonds. So let's look at three of the most useful redox reactions for carbonyls. The first one will be reduction of aldehydes and ketones to alcohols. And we'll look at the generic examples first, then we'll look at specific examples. This is either R or H. R if it's a ketone, H if it's an aldehyde. We have to react with some kind of a reducing agent, something that's going to add hydrogen to form the alcohol. The next set of reactions that we'll look at will be the reduction of carboxylic acids and their derivatives, again as a generic reducing agent. And these will sometimes reduce to the aldehyde and will sometimes reduce all the way to an alcohol, depending on the reaction. The third example is the oxidation of aldehydes. So this is going to be a generic oxidizing agent now, up to a carboxylic acid. Remember that you can't oxidize ketones up to a carboxylic acid because they don't have a hydrogen here that can leave. So if we have a ketone, we can't do this oxidation. Let's look at section 20.4, which is reduction of aldehydes and ketones to alcohols. So we need a reagent that's going to be our reducing agent, and there are two common ones that will do this. They are lithium aluminum hydride and sodium borohydride. They both react very similarly. Let's take a look at what lithium aluminum hydride looks like. We have a lithium positive ion, then we have aluminum hydride minus. Hopefully you remember that aluminum typically makes 3 bonds. So if there's a 4th bond to hydrogen, this is our hydride, this has got a negative charge. So lithium plus AlH4 minus. Really, all of this is, how I would view this if I were you, is this is a hydride donor. The whole molecule of lithium aluminum hydride is just there so that it's something that will be a good hydride donor in nucleophilic addition or nucleophilic acyl substitution reactions. Sodium borohydride is very similar, in fact nearly the same. You've got an Na+. Boron once again makes 3 bonds typically. So if I have a boron with 4 bonds to hydrogen to it, this now has a negative charge, and once again this can be seen as just an H- donor, something that will add H- to our molecule. Of these two, lithium aluminum hydride is a little bit stronger, hydride donor. since the aluminum hydrogen bond is a little bit more polar than the boron hydrogen bond. So let's look at the mechanism for how this works. So I'll just take an aldehyde. It could be an aldehyde or a ketone. I'll use lithium aluminum hydride. If I react it with lithium aluminum hydride, you can just write H- above it, and because really what happens is H- comes in and adds. Now we have to go back to ask ourselves the same question we always ask: who has electrons and who wants them? The hydride, hopefully that's pretty clear, has the electrons. It has a negative charge. And so who on our carbonyl wants electrons? Okay, this is our nucleophile, the hydride, and our carbon is going to be the electrophile. So if the hydride adds there, we'll have too many bonds to this carbon unless we break the pi bond and have it go out onto the oxygen. Now if you remember from our discussion of the competing mechanisms, the nucleophilic addition versus nucleophilic acyl substitution, the next question we have to ask is, do we have a good leaving group or not? Are either of these a good leaving group? And the answer is no, we do not have a good leaving group. And since there's no good leaving group, we can't do a nucleophilic acyl substitution. All we can do is a nucleophilic addition. So now we just have to add some water, and we get our final product, which is the alcohol. If you want, you can draw it without the hydrogens, or you can add the two hydrogens in, if it helps you to keep track of what the changes were in the molecule. Okay, so effectively what we did is we added H2 across this double bond. We had one hydrogen on each end of this pi bond of the carbonyl. And so this overall reaction is a reduction. We added hydrogens. We have more carbon-hydrogen bonds than we had in the starting material.